Okay, so let's continue. So can you hear me?
Yes, sir. Yes, sir.
Okay. So we have a 3 by 3 matrix for ML equals 0 value, for L equals 0, 1, and 2. And we have a 2 by 2 matrix for ML equals +1 and -1 value for L is equal to 1 and 2. Okay. And of course, initially, all these states had 2n squared fold degeneracy. And we would have expected the entire problem to be dealt with using degenerate perturbation theory. But because of the parity, we actually can break this bigger problem into smaller pieces. Okay. And instead of working with 5 states of L equals 2 plus 3 states of L equals 1 plus 1 state of L equals 0, using all that stuff, with of course 2 values of spin states, we would have had some 18 by 18 matrix to be solved, but that's not the problem. That's not how it actually works out. It simplifies quite a lot for various reasons. One of them is that the spin quantum number is untouched, and second thing is that the parity breaks the problem into smaller pieces. Okay, so this would allow, of course, to lift the degeneracy from 2n squared fold down to some lower thing, but it does not completely kind of eliminate the degeneracy. It only lifts it partially. Okay, but nevertheless, at least the problem is under control. Okay. Now one thing that we need to understand here is that the hello. Yeah. So one thing we need to understand is that the perturbation EEZ is not a stable perturbation, in the sense that, it's a linear potential, right? So therefore, it is not bounded from below. Okay, so it's kind of an unbounded perturbation. Okay, and so if you go for large enough negative values of Z, okay, then the energy that this would kind of generate is lower than the bound state energy. Okay, so therefore this kind of perturbation can generate instability in the bound state spectrum of the problem that we are looking at. Okay, so if you put an atom in the external electric field, then whatever states that you are looking at, whatever spectrum that we studied by solving these kind of problems, are all approximate bound states. Okay, and one really needs to ask a question as to under what circumstances would this bound state be unstable. Okay, and of course, whenever the bound state is unstable, that would mean that. Hello, can you hear me?
Your voice is breaking, sir.
Yeah. So let me kind of try it again, because it's on the phone network. Institute network is still off. I hope it is little better. If not, you tell me, I'll go outside. Maybe the network will be little better. Should I go outside? Hello?
Sir?
Should I go outside for a better network?
No, sir. No.
It's audible, right?
Yes, sir. Yes, sir.
Okay. So let's continue then. So when one says that the bound states are unstable, that means the electron in that state could escape. Okay. But if an electron escapes from the bound state, then an atom would convert from a neutral atom to an ion. Okay. So a process of that kind is typically called ionization. Okay. So what we will do today is to study this process of ionization. Okay. So we want to compute the ionization probability. Okay, and to do that, let us consider the ionization of single electron atom in an uniform electric field. Okay, so electric field induced ionization in this particular case. So our potential is the usual Coulomb potential that we have already solved exactly, plus this field generated by the external electric field. Okay, and as I said, that because this potential is linear, it is in fact going to affect uh, the form of this potential for large values of z, uh, because for large positive values of z, it is large potential, large negative values of z, it is large negative potential. Okay, large positive versus large negative. So let's look at the figure to get a picture as to what it is doing. Okay, so the figure would look something like this. Okay, so this is the potential. We are looking at it as a function of z only. Okay, and in one direction, usual potential was like something which was kind of going asymptotically to zero. Okay, that is like 1 over r potential would have gone like that. Okay, and it would have gone like that in z negative z direction also. Remember, because in the radial case, r takes only positive values, but if you plot it in Cartesian coordinates, then you would see that the potential is kind of asymptotic uh, to zero in both directions. Okay, but because of the electric field, it kind of eventually looks like a straight line of this kind far away. Okay, in one direction it goes up, and in another direction actually goes down. Okay, this amber dotted line, or amber dashed line rather, is the line corresponding to the bound state that we are looking at. Okay, okay, I have drawn it arbitrarily, but it is supposed to say it's a ground state energy. Okay, now if you had the original potential, if there was no electric field, then this state is exactly uh, stable, simply because asymptotic energy of the potential is zero, whereas this energy is negative, some negative number. Okay, so clearly the state is kind of stable. The wave function beyond this point is going to be exponentially decaying, and it will just vanish at infinity, whether you go to positive z direction or negative z direction. But if you apply electric field, then uh, in this direction the wave function is stable. Okay, but not in the negative z direction, because in negative z direction this wave function is going to kind of have oscillatory behavior beyond this particular point. Okay, now of course classically this state is still stable, simply because it cannot penetrate, it cannot overcome this potential. But we know quantum mechanically there can be tunneling. Okay, so therefore, although the classically the states are stable, quantum mechanical behavior of these states would be different. Okay, okay, so for any fixed Brown state energy, now suppose instead of looking at this energy level, suppose there was some energy level at this level, point. Okay, then that energy level would be stable in this direction anyway, but in this direction it would develop instability, but for far further out in this direction, not somewhere here, but like for larger negative values of z. Okay, but nevertheless, at some sufficiently large negative value of z, even that state would be unstable. Okay, so therefore, uh, choose any fixed bound state energy. Okay, there always exists a finite probability of tunneling in the negative z direction. Okay, and this is what we would call ionization of the atom. Okay, okay, so what we will do is to try to determine, actually we will not determine the ionization probability, but we will kind of get estimate of determination of ionization probability by reducing this problem to a one-dimensional problem. Okay, now to do that, we'll have to find right kind of coordinates in which you could reduce this problem to a one-dimensional problem. Okay. This is something I think I had given as a homework assignment, but we will do it again here. Okay. So what we will do is first we will convert the problem into a one-dimensional problem. Okay. And then we will compute tunneling probability within the what is called the Wkb approximation. Okay. So although we will not be you know dotting all i's and crossing all t's in this computation, but at least gives a picture as to how you would go about doing this computation. Okay, that is what we will really do. When one wants to actually do this computation, it's the same technique. It's just that like you'll have to fill in the gaps as to correctly normalize wave functions, and across the regions you match the wave functions, uh, wave function on the left to right, and stuff like that. Uh, Something we will not do explicitly today. Okay, but uh, that is more of a technical computation than the conceptual part of it. Okay, fine. Now, first thing that we notice is that the electric field has already broken the spherical symmetry, because electric field is EEZ, and Z is a spherical vector, and you know that vector cannot preserve spherical symmetry because it has a direction, and therefore it has a chosen axis, and therefore it can at best have axial symmetry, cannot have spherical symmetry. Okay, so electric field would existence of electric field means we have broken the spherical symmetry. Okay, so as a result, whatever we had done with say single electron atom problem, say in quantum mechanics 1 course or something, namely using spherical polar coordinate system, we cannot use that anymore, simply because the electric field has kind of broken that symmetry. Okay, fine. So what we will do is we will use what are called parabolic cylinder coordinate system. Okay, so here are the parabolic coordinates. You consider psi, eta, and phi as the parabolic coordinates. Uh, Phi is the coordinate along the cylindrical direction, uh, and xi and eta are semi-infinite coordinates. Okay, they will take value from 0 to infinity. And our Cartesian coordinates are, oops, okay, I meant sine phi, not sigma. Um, so I'll correct it. But our Cartesian coordinates are square root of xi eta times cos phi, y is square root of xi eta times sine phi, and z is equal to half xi minus eta. Okay, uh, so if you look at this, and if you say x squared plus y squared plus z squared, which is same as r squared, then you'll notice one thing, that cos squared phi plus sine squared phi will kind of go away. You get xi eta factor, and z squared will give you kind of half a quarter of xi minus eta whole squared. You can put all of them together, you will find that r is xi plus eta by 2. Okay, uh, it's just a straightforward computation. Okay, so the radial coordinate which is there in our problem, okay, can be written in terms of the parabolic cylinder coordinates as xi plus eta by 2. Okay, whereas z, which is the other coordinate which appears in our potential, okay, can be written as xi minus eta by 2. Okay, so in that sense, both these quantities can be written in terms of xi and eta in terms of simple functions and not too complicated thing. Okay, so here's an exercise that if you choose this coordinate system, okay, with of course typo corrected, then you can show that the Laplacian acting on the wave function psi can be written in this particular form. Okay, uh, so this Laplacian in Cartesian is trivial. D squared by dx squared plus d squared by dy squared plus d squared by dz squared acting on psi, and then just use this change of coordinates and show that Laplacian can be written in this particular form. Okay, The potential can be written in this form is kind of trivial. There is really no work because R is equal to this and Z is equal to that. You just have to just plug in. Okay. Fine. Any questions at this point? Okay. Hopefully you are still connected. Okay, so the Schrodinger equation that we would write down would still have a rotation symmetry uh, about the z-axis. Okay, because if you rotate about z-axis, the radial uh, part of the potential is invariant under that, and z-axis, of course, itself doesn't rotate, and therefore Ez would also be invariant under that. Okay, so what we could do is to kind of try to use this fact and z directional rotation symmetry would tell us that the phi coordinate, which is the periodic coordinate in parabolic cylinder coordinate system, okay, would have the wave function splitting into either the I M phi kind of thing. So we will use that, and we can attempt the uh, form of the wave function of this type. There's a small typo here, but form of the wave function of this type, where we write down the angular part to be e to the IML times phi times a function of xi times a function of eta. Okay. So the total Schrodinger equation is, of course, this plus v times psi kind of piece. This, of course, is a minus h bar squared upon 2m and stuff like that. Everything can be put in correctly. But you know how the whole Schrodinger equation would look like if you know this and this. Okay. So we are going to attempt this kind of separation of variables, okay, and substitute this form of psi inside this corresponding Schrodinger equation. Okay, so what we will do is that we will take this. There is a xi plus eta sitting in the denominator. We will multiply by xi plus eta everywhere, and we can separate the variables, and you get the equations of this type. Okay, so if you substitute this and just kind of carefully work through it, you get a term. Okay, so remember, like, you need to take care of a few steps. Substitute this psi inside the Schrodinger equation and divide that entire Schrodinger equation by psi again. Okay, now, that is not really essential, but it is a good thing to do to see that the variables are actually completely separated. Okay, so if you do that, then you get an equation which looks like this. Okay, so this is an exercise. You can check this one. Okay, so now you see that the first line of this equation completely depends on xi, and second line of this equation completely depends on eta. Okay, except the last piece, which is just a constant. Okay, so we are going to distribute this constant in a specific fashion between the first line and the second line. Okay. So the rule of separation of variables is the following, that this is something that we have done in QM1 itself, that you take the first line of this equation and say that that is equal to some constant, and then you take the second line of the equation and you say that that equals, the second line of the equation is equal to the same constant but with a minus sign, such that when you add these two fellows, that two constants cancel and you get this equation. Okay, so which is what we'll do. Okay, we separate these two things. We define the first line plus a constant equals 0. Second line plus another constant is equal to 0. And then demand that the sum of these two constants is the constant quantity staying around here. Okay. So there are various different ways of doing it. This is one particular way of doing it. Okay. You could have, of course, put a constant nu here and a nu plus zme squared on this side. It's all they are all the same basically. In this particular case, what you have is two differential equations and one constant equation. Okay, that is how it is. Fine. Now, there is one more thing that you should notice, and we will kind of utilize this today, and that is that if the electric field was not on, okay, that means this curly E is set to 0, then these two equations are actually identical, okay, except, I mean, if you replace F by G and Xi by eta, these equations are essentially same, okay, ml squared upon 4 xi, ml squared upon 4 eta with a minus sign, me by 2 times xi, me by 2 times eta with plus sign. This piece goes away because epsilon is 0, and then even new equals 0. It's like, they are essentially identical equations. Okay. But if the electric field is 0, then actually you are trying to solve the original hydrogen atom problem, right? Okay. So now you notice one very interesting thing in the parabolic cylinder coordinate, which you wouldn't have expected naturally because the problem had a spherical symmetry in the absence of electric field, and you would have therefore naturally used the spherical polar coordinate system. But now you see that in the parabolic cylinder system, one part of the problem is kind of trivial because of the angular symmetry. You write down your wave function as it's the im phi, and the other two coordinate equations are identical. So therefore, you really have to solve one differential equation and not two. Okay. So in that sense, this problem, hydrogen atom problem in parabolic cylinder coordinate system is in fact simpler than solving that problem in spherical polar coordinates. Okay. So suppose we start with the external electric field to be 0. Okay. Then we should be able to get the hydrogen atom problem. So let's see how we get it. Okay. So first thing that we could do is we can rescale the coordinates, okay, in such a way that we can set the coefficient in front of a linear in xi or linear in eta coordinate to be some fixed number. Okay, I will choose that to be say 1/4. Okay, now to get that thing as one, why am I saying 1/4? Well, there is nothing very special about 1/4, but what I really want is that this equation should look more like a Schrodinger type equation. So if you want it to look like a Schrodinger type equation, then you would want the quantity sitting here to look to be 1 over 2m. Okay. So what you want to do is to actually multiply this entire equation by 1 over 2me. So if you multiply the whole thing by 1 over 2me, then it kills this m times e and it gives you a factor of 4. Okay, that is the reason for getting this. But once you do that, then you have a factor of 1 over 2m e actually, but nevertheless 1 over 2m factor sitting around there. Okay, so it kind of gives this equation a semblance of Schrodinger type equation. Okay, it's not really necessary, but one can always do that. So this rescaling, okay, to get the coefficient in front of xi to be 1/4 would correspond to choosing a new variable rho written by rescaling xi by beta, and beta is square root of minus 2m. Okay, so if you do that, then your equation is going to look something like this. Okay. Notice one thing, that I have multiplied this entire stuff by f. Okay. In this form, it was 1 over f times something. But if you multiply the whole thing by f, then there's a f sitting around all these terms. Okay. And because there is a beta factor sitting around, the original new one is replaced by lambda 1, which is lambda 1, which is mu 1 by beta. Okay, so this is how this equation is going to look like. Okay. Fine. Now what we could do is that, I mean, it's not very surprising given that those two equations are identical. You can do the same trick with the eta equation. Okay. All you have to do is to replace nu 1 by nu 2, and therefore lambda 1 by will be replaced by lambda 2. Okay. Fine. So let's look at this equation. Okay. and ask how is this equation going to behave in the neighborhood of rho equals 0. Okay, and clearly because there is a fact 1 over rho sitting around in one of the expressions here, rho equals 0 is a singular point. Okay, and one can check that it's in fact a regular singularity. Okay, so since it's a regular singularity, what we should be looking at is to write down a Frobenius series-like solution in the neighborhood of rho equals 0. Okay, fine. On the other hand, if you look at rho equals infinity, then remember there is a solution which grows as rho, and then there is a piece which goes as constant. Okay, and as a result of these two quantities, you will find that your solution is actually going to grow at infinity. This is the most dominant term in that growth. Okay, and this term will tell us that the solution actually has irregular singularity at infinity. Okay, now that is just as well because we want our wave function to be exponentially damped as you go to large values of the independent variable. Okay, so in this particular case, the independent variable is rho. Okay, and if it is falling exponentially, then of course what we would say is that this kind of wave function is square integrable. Okay, is that fine? Okay, so what we'll do is we can do this analysis, and what we can show, okay, is a simple exercise that near rho equals 0, the function f will have a dependence rho to the ml by 2. Okay, and near rho equals infinity, the function has a dependence exponential minus rho by 2. Okay, now it's not a very difficult thing to do. What you need to do is the following, that as rho goes to 0, this term is going to be small. Okay, this term is constant, but it doesn't kind of, is not dominant. Whereas this term is important because as rho goes to 0, it becomes more and more dominant. Okay, so what you do is you keep only this part of the equation. Okay, and study the solution by ignoring other terms and obtain approximate solution near rho equals 0. And because you have a factor of ml squared by 4, it's kind of easy for you to guess that it must be, the behavior must be rho to the ml by 2. So that you differentiate twice, it will give you ml squared by 4. Okay. Now, of course, if it is rho, if you think that if it is rho to the ml by 2, then once you differentiate, it will become ml by 2 minus 1, and therefore you should get a factor which is ml by 2 times ml by 2 minus 1, which is correct, of course. But and it will not cancel this ml squared by 4, but because of this factor of rho, you actually reinstate the power of ml again. Okay, so after differentiating rho by rho, f would have had a dependence rho to the ml by 2 minus 1, but that minus 1 is compensated by this rho, to put it back to ml by 2, and the second derivative gives you a term of this kind. Okay, and you can show that that term would kind of naturally cancel. Okay. Fine. So that is kind of, approximate solution in the neighborhood of rho equals 0. In the neighborhood of rho equals infinity, this term is going to be subdominant simply because rho goes to infinity, it just vanishes. This term is constant at infinity, so it's not going to be is not going to be the dominant behavior. Okay, whereas this term is going to grow. So what you need to do is to look at this piece and this piece. Okay, and looking at these two terms, you can kind of figure out that f as exponential minus rho by 2 is a natural object to look at. Okay, fine. So so you should be able to kind of show that this kind of form of the behavior of the solution in the neighborhood of two singular points that we have noticed uh, can be kind of summarized in this form. Okay. Now, clearly these are just approximate solutions. Okay, in the neighborhood of, I mean, or rather, they are exact solution to approximate equations. Let's put it that way. Okay, because you ignore this term, take only first two and solve near rho equals 0. Look for exact solution to that equation, but the equation itself is approximation to the original equation. Okay. Similarly for at infinity. Okay. So what we will do is we will use this fact that in the neighborhood of these two singular points, the solution behaves this way. Use this to write down a solution which takes the form like this. Okay. So what we have is rho to the mod ml by 2 times exponential minus rho by 2 times an infinite series a n rho to the n. Okay. Fine. So what we want to do is to substitute this as a solution in the differential equation that we have, and ask how we determine the coefficients of this series, namely ans. Okay. Now the point is that all you need to do is to kind of plug this back up into this equation. Okay, and collect powers, fixed powers of rho. Okay, whatever are the coefficients sitting in front of those, you kind of look at those coefficients and set all of them to 0. Why 0? Because right hand side is 0. Okay, so each power of rho should have vanishing coefficient because right hand side is vanishing. Okay, so if you do that, then you essentially get some kind of a recursion relation. Okay, you need to solve that recursion relation to determine an, and typically because it's a recursion relation, it basically tells you how you determine an in terms of, say, an minus 1, an minus 2, and stuff like that, finite number of lower ans. And of course, an minus 1 is determined in terms of an minus 2, an minus 3, and stuff like that. Okay. Given that the equation is linear differential equation, okay, it is linear in f everywhere, a0, which is the first coefficient, cannot be determined. Okay, only thing that you know is that a0 is not equal to 0. So it can be any number. And the reason why it can be any number is because if f is a solution, then alpha times f is also a solution, because this alpha just factors out of the whole equation. Okay, and therefore a0 cannot actually be fixed. Okay, so whatever recursion relation you get, you choose a0 not to be 0 and write down all a1, a2, a3 in terms of a0 through the recursion relation. Okay. Now, of course, in quantum mechanics, you don't want to do that kind of stuff because you want square integrable, normalizable wave functions. So you actually normalize those that determine what is the value of a0. Okay, because you want the area under the curve to be equal to 1. Okay, fine. So what we have to do is that we could determine all these ans, but typically what happens is that the coefficients an are growing very fast, and if you keep those ans non-zero for all values of n, then this series actually can be summed, and the answer and the summation of that series would turn out to be exponential of rho. Okay. If that answer is e to the rho, then that will multiply e to the minus rho by 2 to give you the answer e to the plus rho by 2. Okay. E to the plus rho by 2 is not a good thing, simply because we want our wave function to fall off to 0 at infinity, and that was one of the reasons why out of two possible solutions at rho going to infinity, we picked up only one of them, namely exponential minus rho by 2. So if you want to preserve this behavior, we would say that this series actually terminates for some value of n. Okay, that means you say that an for some value of n vanishes. Okay, and that vanishing condition imposes a constraint on the parameters that are appearing while determining all these all these ans when we were when you substitute this wave function back into the Schrodinger equation. Okay, so here's an exercise. This thing that when you demand that the series terminates for some power of rho, say rho is equal to some n is, or rather n is equal to some n naught, okay, then that condition would tell you that lambda 1 is equal to half of ml plus 1 plus n1, okay, where n1 is an integer taking values 0, 1, 2, 3, dot, 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 dot. Okay, we can do similar exercise for the function g. Remember, f is a function for in the variable c or rho. Okay, g is a function which is written in terms of variable eta, which of course we will kind of rescale to something else, say something like sigma. Okay, but you could kind of write down that solution also, and that would give you lambda 2 is equal to half ml plus 1 plus n2, where n2 takes values, integer values 0, 1, 2, 3, and so on. Okay, any questions here? Okay, so if not, then let's go ahead. Uh, Remember, like lambda 1 and lambda 2 were related to nu 1 and nu 2 through beta. Okay, so beta times lambda 1 was nu 1. And nu 1 and nu 2 had to satisfy a constant, namely nu 1 plus nu 2 is equal to Zm e squared. Okay, so what we'll do is we'll impose those conditions on whatever solution that we have obtained here. Okay, so his form lambda 1 is this, lambda 2 is this. Okay, good. So we substitute Z m e squared is equal to nu 1 plus nu 2, which is same as beta times lambda 1 plus lambda 2. Okay, but beta was equal to square root of 2 me times of course lambda 1 plus lambda 2. Okay, so what we will do is we'll take this equation Z e squared m is equal to square root of minus 2 me times lambda 1 plus lambda 2. Okay, we know what is lambda 1 and lambda 2, which are written out here. Plug them in and invert this relation to determine E in terms of all other quantities. Okay, is it fine? Okay, so if you do that, then you will find this to be the solution. Okay, that the energy spectrum is, because of the square root, some of these factors are easy to guess. Z squared e to the 4m times m upon 2. Okay, it would have been m squared, but there is a 2m sitting on this side, so that's why it gives you m by 2. This minus sign comes from here. Okay, times 1 over ml plus 1 plus n1 plus n2 whole square. Okay. Those are the factors which are coming from these quantities. Okay, if you take lambda 1 plus lambda 2, then it is kind of easy to see what we are getting here. Okay. Fine. So now we can compare this spectrum with the spectrum that we obtained in the spherical polar coordinate system. And remember, in the spherical polar coordinate system, you of course get z squared e to the 4m upon 2 kind of quantity, but that is multiplied by 1 over n squared, where n was a principal quantum number, and and we had 2 times n squared fold degeneracy in the problem. Okay, so that principal quantum number can now be identified with mod of ml plus 1 plus nl n1 plus n2. Sorry. Okay, so here's that identification. Okay. Fine. Uh, so what you need to check in this exercise is that remember the spherical polar problem would have had the principal quantum number, and that would have determined the degeneracy of the uh, state, and the degeneracy was equal to n squared. It is equal to 2n squared really, because the factor of 2 came from the 2 spin degrees of freedom. Okay, but if you kind of temporarily ignore the spin degrees of freedom, then the degeneracy was just n squared. Okay, and that was kind of obvious in the spherical polar coordinate system. Okay, what you need to show in this exercise that if you write it in terms of n1, n2, and excuse me, and ml, okay, the degeneracy continues to be n squared. Okay, that's an interesting exercise. Okay, so any questions at this point? Okay. So of course, the ground state corresponds to taking the smallest possible values of n, n1, n2, and ml. Okay. ml, of course, it's a mod of ml, so the smallest value that ml could take is 0. The smallest values n1 and n2 can take is 0. Okay. And notice that the principal quantum number starts from 1. So taking this to be 0, n1 to be 0, n2 to be 0 would give n is equal to 1. Okay, so that would be the ground state of the problem. Okay, and of course you can substitute that value down there, and you'll find that the ground state energy is z squared e to the 4 m by 2. It's precisely what we had gotten when we were studying it in the spherical polar coordinate system. Okay. Now, of course, the ground state wave function is kind of trivial to get, because the behavior of the of the wave function tells us that. Okay, so let me just go back and show it instead of saying this. Okay, so or maybe any one of these two. So since we are taking ml to be equal to 0, there is no rho dependence of this type. You have e to the minus rho by 2. Okay, and you are looking at a state which has kind of no nodes. Okay, so therefore n is equal to 0 here. Okay, so that gives you just a number. Okay, so and this is how the behavior would be both for f and g. Okay, so that is why our wave functions are just going to be e to the minus rho and e to the minus, sorry, not rho, e to the minus psi and e to the minus eta. Okay, this is actually rho. This thing beta c is same as rho. Okay, fine. So the wave function is just a product of these two quantities up to some normalization factor. Okay, fine. So what you can, here's another exercise. What you can do is to determine the integration measure in the xi-eta coordinate system. Remember, the integration measure in the Cartesian coordinate system is trivial, right? Dx dy dz. Okay, and there is no additional factor sitting around. Okay, and you know how to write down x, y, z in terms of psi, eta, and phi. Okay, so you can use that relation and determine what is the integration measure, or what is the definition of a volume element in xi, eta, phi coordinate system. Okay, once you determine that, then using that integration measure and this form of f and g, well, you don't have to only look at the ground state. You can look at any arbitrary energy state, so something like this. Okay, you can try to determine the normalization of the wave function. Okay, so that is the exercise. Fine. So what we have done so far is to determine the ground state wave function in the absence of external electric field. Okay. Now what we will do, so this is like solving a hydrogen atom problem with a new coordinate system. That's all. Okay. So what we'll do now is to actually turn on the electric field and ask what is the effect this electric field would have on the ground state of the hydrogen of the single electron atom problem. Okay. So uh, now let's go back. I had kind of pointed it out, but let's look at it once again. When the electric field is non-zero, then these two equations are not identical because there is a -1/4 factor with EEM times I squared and +1/4 factor with EEM times eta squared. So whatever advantage we had in the absence of electric field is lost simply because these two equations are not identical. Okay, so whatever results that we had earlier need to be revisited to see how the wave functions are going to look like. Okay, but as I said, what we are going to do is to mostly work in Wkb approximation. Okay, so what we'll do is that, like, we'll first bring the equation. So this is the equation. Let me just show it to you again. So this is a form of the equation. So if you try to expand this stuff, okay, of course there's an additional piece also now because the electric field is non-zero, but that is not what I'm concentrating on right now. Suppose you open up this bracket, then you will see that like dd rho would act on rho. That will give you a first derivative of f piece. Okay, and when dd rho doesn't act on rho, then it gives you rho times the second derivative of f. Okay, so this equation contains second derivative of f piece and the first derivative of f piece. Okay, so but that is something we know from quantum mechanics 1, that if you get a equation which contains second derivative and first derivative, there is a all you need to do is to kind of write down wave function in a specific fashion so that you can reduce that equation to a second order differential equation without a first order derivative term. Okay, so that can be done in this particular case by doing the following definition or redefinition. Okay, so the f of c that we were looking at earlier, okay, that f of c would be written as c to the minus half times a new function of c. Okay, and similarly g of eta would be written as eta to the minus half times capital G of eta. Okay, so if you do this, then one can kind of bring the equation in a little bit simpler form by eliminating the first order differential equation. Okay, so that is another exercise thing, and that is you take the equation that I was showing you earlier. This, or rather, this kind of equation. Okay, do two-step computation. First, you do this rescaling, okay, and write it in terms of row variable, and then you do this transformation. Okay, this transformation. So if you do that, then your equations are going to look like this. And again, you will see that these equations are almost identical except for the electric field factor, okay, which is where they switch sign. Of course, we have a nu1 and nu2 sitting in front of f and g, and 1 over and 1 over eta factor comes because second derivative piece would have had a xi and a eta sitting around, and our typical technique is to keep the coefficient of the highest derivative term to be 1. Okay, and because of that, you have like different factors sitting around out here. Okay, fine.
Yes,
now,
sir.
Yes.
There's a change in sign in the factor of So there was like in F there is minus E and there's plus E in G, the equation of G.
Equation of G.
Yeah, the last term. There is
This one.
minus EM E and for G it is plus EM.
Yes.
So the solutions will be qualitatively different for F and G, right?
Yes. You mean the behavior is different? Is that what you mean?
Yeah,
Yeah,
yeah.
yeah, definitely, definitely. In fact, that is what we are going to capitalize on.
Okay.
Okay. So, so when the electric field was zero, these equations were identical. But when electric field is non-zero, then these equations have a different behavior. Okay. We will use that fact. In fact, you are saying something else?
So asymptotically, when we combine these two solutions, when we write the full solution, the
Yes.
product of F and G,
Yeah.
then we should get something like Z in the exponential or something.
Z.
There should be because in polar coordinate we saw that Z was like a dominating term in at infinity.
Yes. Yeah. Yeah.
So it
Yeah.
should
So if you go, you want to, I understood. If you want to go back to the Cartesian coordinate system,
yeah.
that's what
So
you're saying. Yeah, yeah,
what
yeah. Then of
kind
course
of
there's a Z.
solutions will be there?
Yes,
Yeah.
yes. True, true. That's what we will see. Okay.
Okay.
So of course we will not go back to Z coordinate because whatever computation you would do, after all, this factorization is a factorization because Z is xi minus eta. Really, no.
Yeah. Yeah.
Remember, so that is why there is a relative sign between them, right? So if you want to go back to the Cartesian coordinate system, you will see that the if final wave function will have a Z dependence. Okay, but what we will see is that, like, it's easier to solve it in this set of coordinates.
Okay.
Okay, yeah, fine. So with these redefinitions, what we managed to do was to get rid of the first order differential equation, the derivative part in the differential equation, and we have equations which look like this. If you really want to be pedantic, you could kind of divide by 2m so that it really looks like a Schrodinger equation. Then that 2m will get rid of this, and you get e by 4 factor sitting around here, and other pieces you can try to interpret as potential pieces. Okay, uh, but I mean, we will use this fact at some point that we are dividing by 2m everywhere, just to kind of get this factor to be e by 4. Okay, fine. But our interest is really in ground state to start with, and if you do that, then you're looking at ml is equal to 0. Okay, and nu1 and nu2 is equal to beta by 2. Okay, which is zm e squared by 2. Okay, now it's not immediately obvious why this would be the case, but if you go back and check uh, here, uh, or maybe further back, if you look at the ground state and if you set ml is equal to 0 and n1 and n2 is equal to 0, then lambda is just half. Okay, and lambda is equal to half tells you that nu1 and nu2 are beta by 2 each. Okay, so that is what we are doing here. Okay, so nu1 and nu2 are beta by 2, and beta is of course zm e squared by 2. It is not immediately obvious, but what you could do is to do the following thing, that you write down beta, which is defined to be minus 2 me naught, where it is actually minus 2 me, but we are looking at ground state energy, so we substitute ground state energy factor. Ground state energy factor is this. Okay, so this minus sign goes away, the factor of 2 goes away, and you get z squared e to the 4m squared, whose square root is just this quantity. Okay, so that is why you get that. Okay, is that fine? Okay, so let's look at the potentials now. Okay, now remember the potential written was written in terms of r and z initially, but now we know how to write down the potential in terms of xi and eta, and it's written out here. Okay, uh, it is kind of hidden in this kind of particular form. there's some 1 or 2m needs to be divided, but it basically takes this particular form. Okay. So what we will do is we'll just try to see how these potentials are going to look like. Okay. And decide as to what is the problem we are really interested in. Okay. So here's the potential V1. Okay. So V1 takes, if you try to plot it, it takes a form which is like this. Okay. And this dashed amber line is the energy E by 4. Okay. Remember I was telling you that like you would have, if you divide by 2m, then this will become E by 4. So we just want to ask where the E by 4 is sitting around. So it's here. Okay. So clearly in the xi coordinate system, you can see that the problem is completely stable. Okay. By stable, I mean that if this is the energy level, then this energy level is uh, a bound state energy and it is never going to decay. Why? Because the potential is just going to grow and go to infinity as I goes to infinity, and therefore there is no chance of this state ever tunneling out of this potential. Okay, and therefore in the xi direction the bound state problem is exact. Okay, and therefore we don't need to worry about what. Well, I shouldn't say exact, but the bound state problem is stable. Okay, it is not going to decay. Let's look at V2. Okay, so V2 takes the form which is like this. Okay. And these are not approximate plots. I have just plotted these precisely these functions by putting some values of z and m and e and so on, and it plots in this particular way. Okay. So here is a potential in the eta direction. Okay, and clearly the e by 4 state, okay, is not stable. Okay, classically, of course, this is a region where the bound state was sitting around, and classically is of course stable. There is no question about that. But quantum mechanically, if you go far out in eta direction, then there is a place where you cross this potential again, and there is a finite probability for a particle with energy E by 4 to tunnel across and go all the way to infinity in eta direction. Okay, fine. So here's other conclusions that we had already drawn. Okay, that the plot involving V1 as a function of C is stable. Okay, nothing great happens. The plot involving V2 as a function of eta clearly has a tunneling possibility. Okay. Now, what is the downward slope here? That depends upon how strong the electric field is. Okay, if the electric field is strong, this will kind of fall off faster. Okay, and if that is what happens, then this barrier, okay, will start shrinking. Okay, so higher would be the slope of this downward line for a stronger uh, electric field, and as you turn the stronger and stronger electric field, the tunneling probability starts increasing. Okay, so that is how this problem would be set up. Okay, fine. Any questions? Okay, so what we have to do now is to kind of set it up in the Wkb approximation. So, I mean, it's a small thing, but I would probably defer it to the next class, uh, just to kind of explain what we will kind of divide this entire problem into 3 regions. We are going to ignore this part of the problem simply because this part of the problem clearly tells you that this state will, the electron in this state will never escape to infinity, and therefore there is no chance of ionization in this direction. Okay, if there is any chance of ionization, that is if the electron escapes in eta direction. Okay, so we'll look at only the eta direction. Okay, so what we are going to do is we are going to keep the left region to be the bound state region. We are going to kind of interpret that as a bound state region, and then remaining regions will be divided into 2 parts. One would be called region 1, the other will be called region 2. Okay, and what we want to do is to define the bound state problem we know. Okay, we have already done that computation. Okay, we want to write down wave functions in region 1, wave functions in region 2, And of course, we know the wave function corresponding to the bound state, and we want to set up a WKB answers for this. Okay, so what? So of course, we are not going to solve the stuff explicitly, but I'll tell you as to how you set it up. That's all. Okay. So, but maybe in the next class. Any questions? Hello. Any questions? I hope I am connected.
Yes, sir. Yes, sir.
Yeah. Okay. Thank you. Okay.